So our next topic focuses back again on vector data, and we'll be exploring the fundamentals of the data model, how to edit vector data, both in terms of lines and some fundamental ideas about information contained within tables, and how to link different kinds of information together, and then how to query that information out of tables to give both visual and table based answers uh, to questions that you might have of the data. So, here we've introduced vector data before, but we're going to get into a lot more details related to the management of this type of geospatial data. Recall that the vector data model is essentially an XY graph linked to latitude, longitude, or some other coordinate system describing locations on the Earth's surface. Vector data can be simple points, which are point locations in space. It can be linear or lines. Lines are composed of points known as nodes with a start node and then a sequence of vertex points or vertices that describe the linear feature across space, and eventually an end node that denotes where that line terminates. Polygons are composed of a series of vertices, that encompass the area and describe that area. Okay, so there's points, lines, and polygons again. And we can attach tables to these points, lines, and polygons that contain attributes describing variables. So any environmental variable that you can think of, or any human demographic variable that can be described with a point, line, or polygon, that's what is contained within vector data sets. And these are pretty handy, as you can see, for storing discrete objects on the Earth's surface, points, lines, and polygons, as opposed to complete surfaces. Raster data is better in many ways at describing and analyzing complete surfaces. Vector data is being very accurate and precise, and if it's truthful, um, then it's very useful in our geospatial analysis. The tables that we can attach to them can store thousands, if not millions, of variables and attributes. Vector data is, as should be kind of obvious, very flexible and useful for cartographic representations of areas. If you think back of all the maps you've ever used in your life so far. In terms of storage, vector data tends to occupy less storage physically on a hard drive or another storage medium. And they're very, very much superior to raster data for calculating areas, lengths of features, and connectivity between features on the Earth's surface. So we can't do everything with vector data, but vector data is very useful, very handy for describing and analyzing just about anything that we can think of that relates to the Earth's surface that can be boiled down to point, line, or polygon um, representation. Here's a very simple example using the vector data model to describe the landscape on the left using the vector data model on the right. So on the left, we're saying that's the real world. Here's a stream um, either going into a lake or exiting a lake. We don't really know, because there's no topographic information to tell us which way the stream is flowing. There's a forest. We have an urban area, a city, and agriculture. So those are showing us a linear feature, a polygon feature with a lake, forest meaning an area, urban meaning an area, and agriculture meaning area. So on the right, How would we digitize those things? Well, we'd have the entire agricultural area as a large polygon, and we're only seeing a portion of it here. But to describe the stream, you've got a line consisting of a start node, 3 vertices, and an end node. The lake is described by a start node and a series of vertices around the perimeter of the lake, ending back at the same start node. So start and end nodes for polygons are the same node. You start and end in the same location. Over on the forest, it's another polygon. It's an area describing the forest that has a start node, another series of vertices, the end node, enclosed and describing that area. Another area feature would be the small urban area, in this case being described by a polygon rather than by a point location for the city. So a start node, 3 vertices, and an end node, very small depiction of a small urban area, like a town, um, or in Europe you might call it a hamlet, a very small area. Anyway, here's essentially how vector data works, which is something you're already familiar with from the previous exercises that you've done in the class. Points, as you should remember from high school geometry, they have no dimension, no length, width, or depth. They are just infinitesimally small point features hanging out in space. And so the one thing to remember about how they work in GIS is that every time you see a point location depicted with an icon of some kind of symbol, that symbol is going to be massively, massively, massively large in comparison to how big that point actually is in geographic space, by orders and orders of magnitude. But points are describing location, and we can attribute whatever coordinate system we want to those point locations, and then any information about those point locations that can fit into a table. So here, this is a map showing weather stations in Utah. We can have just the location information alone in the table. If we had ancillary information from those weather stations, we could put in things like annual average temperature, annual average total precipitation, monthly precipitation, monthly temperature averages, daily characteristics, whatever it is. And we can associate those with point locations. So there we go. Lines, again, they have a beginning node, an end node. Here we see a more complex line that splits at an intersection, which would be a node as well when different lines intersect. We call that a node. The points in between are called vertices, or a vertex for an individual point. They're one-dimensional. They have length, and they have connectivity, connection between the nodes and vertices. And so this is the foundation of another data model that's called the network data model that you could use to model stream flow, model city road networks, things like that, and the flow of objects, creatures, or humans, or whatever, along those lines. Okay. At a minimum, though, lines can be simply used to describe the locations of those linear features in space. So, where are the streams? Where are the roads? Where are the landing strips at an airport? Things like that. So an example here would be major road systems in Utah. For some reason, we're using Utah in this series of images. And interstates being depicted with a particular type of a line, a heavy, bold orange line. And we have lots of nodes and intersections and vertices describing that linear entity across space. And then sort of in the background, in the hierarchy of these lines, we see a progression of bold black lines and then lighter blue lines showing secondary highways, maybe state highways, county roads, local roads, things like that. Okay, so again, just an example of a road or a road network being a series of lines together describing those features across space. Polygons, again, they have a start and end node, which is the same location. You start a polygon in one location. You have vertices that are describing that location across space, and it ends at the same node. When polygons share a common border or boundary, they're sharing nodes, start nodes and end nodes. Okay, polygons are two-dimensional, so they've got length, and when those lengths are added together to form the polygon, that's a perimeter, and the perimeter then is describing an area. So the two dimensions are area and perimeter for the polygon. And like points and lines, we can attach lots of different attributes about the Earth's surface, or if we're dealing in other dimensions, in the atmosphere or the ocean, whatever our polygon is describing, we can put that information in there. Here using Utah again, polygons describing the counties, and counties are a series of nodes, vertices, lines that follow the legal boundaries of the county, and then some of the things we might expect to find in a data table for the county: its name, the total area that it encompasses. We might expect to find population characteristics, things at the county level of measurement. So how many people are in the county, how many pieces of property are in the county, average income, average age, things like that. Any kind of demographic information, or any kind of environmental information that was collected or processed and analyzed at the county level could be in a table for the state and the individual counties. So our vector data sets, as we create them, and you will learn how to create them in the exercises for the course, as we create those things, the system is going to automatically be assigning, at minimum, a unique identifier for each thing that we click on and create in the data set, and some other information about it. Its XY location in space, if it's a point, if we're describing lines and creating lines by digitizing lines across space, the start node, the end node. If it's related to polygons, you might have information stored in there related to that. If you actually take the lines to the full extent of creating polygons, you have, again, the unique identifier, and then the lines that comprise that polygon, and then the relationships of adjacency between polygons. There's a lot of information that gets stored when we're creating and editing the data that we'll never see, and there'll be a slide later on that focuses a little bit on those details. But in general, when we're creating or editing data sets that are in the vector data model, at the minimum, we're going to have these things stored in it: a unique identifier for each single point, line, or polygon. With polygons, you also have, or actually with any of these things, with any of these things, points, lines, and polygons, you also may later go back in and put labels on them, so that if you use the labeling feature in ArcGIS, whatever text annotation you put in there, like the name of a city, the name of a river, or for an area, maybe the name of a lake, when you call on the label function, it will be labeled with that entry, and it will appear somewhere related to where that feature is located in space, around the point, somewhere on the line, somewhere within the polygon. One of the main goals when we're creating data sets or modifying them is to maintain logical consistency, or how well the features in our vector data set match or mimic relationships of features in the real world. So, for example, all point locations, no matter if they're point, line, or polygon, should be as accurate as possible to the location of the same points in space on the Earth's surface. That's ideally that's what logical consistency is all about. When we're looking at polygons in particular, there's two things we really need to watch when we're digitizing and describing areas. It's to make sure that the ends and the corners, the point locations, meet at the common vertex as they should, to adequately and accurately describe space, and that adjacent polygons in the same coverage share an identical boundary. We don't have overlapping boundaries. That creates a lot of problems when doing analysis with the vector data model. But the more your data matches and mimics the locations in space, the better your data set's going to be for doing any kind of modeling or analysis using the vector data model. Of course, since humans are involved, there's always errors that creep into the production of vector data model. Here is a sampling of the types of errors that can occur. I'm just going to throw out the names and describe them a little bit. Undershoots happen when the nodes should have come together and didn't, by not completing a line connection or a polygon connection. Overshoots happen when the line gets extended further than it should have been. So it should have terminated perhaps at the node that occurs lower on that particular line, rather than shooting off into space. If you think about a road network, an overshoot would occur when you extend a road too far and you're creating, therefore, a cul-de-sac where there shouldn't be one. If you have a node that's just hanging around and it doesn't really describe things well, and you've missed and forgotten to complete a line or polygon, we can call that a dangling node. Pseudonodes are nodes that someone digitizes when they didn't need to. They're just including too many, for example, along a straight line when two nodes alone would describe the line. They left one extra one in there that didn't need to be there. A line down below on the bottom of this one, a line crossing, no node. So a road intersection where there is no intersection modeled in the data set. That's an error. It's missing one. It's saying there that you've got two roads that don't meet at all, but they cross each other, which is physically a little bit hard to pull off, even though you might have overpasses and underpasses. There's still connections that are occurring there between those road systems quite often. So that's potentially a problem that would need to be resolved in the data set. And related to polygons, you can have a polygon label point in your polygon, and you should, when you're creating those, it may generate one for you at the centroid of the polygon, but you can also put one in yourself to, if you have a particular preference for the location where a label will appear, and if your data set has a full complement of those except for one, you'll have a polygon that when you call the label function, it won't get labeled. So this is just a small sampling of errors. There are a lot more, and if you look into the literature on it, you can find names for a lot of errors. But ideally, when you are digitizing, you will minimize the amount of errors and eliminate them in your work, so you don't have to worry about whether you've got undershoots, overshoots, things like that.